Hey, howdy everybody. So we made it through all of that. Spatial, continuity, varigrams, calculation, interpretation, and modeling. And so now is our opportunity to get into getting some work done. Spatial estimation by kriging and spatial simulation. We'll talk about variogram-based, Gaussian-based simulation methods. So let's get into how do we get to make estimates in space. Let's give ourselves a very simple problem where we have non-stationarity. And you're going to see how critical it is for us to account for non-stationarity when we're making estimates, and it'll follow when we're trying to do simulations later on. And so what we'll find is that in the presence of significant non-stationarity, we would not want to rely 100% on a spatial estimate based on just data and a spatial continuity model. We'd want to incorporate a trend component. So let's give ourselves a very simple problem to demonstrate this. We have V-shell on the y-axis, and we have location on the x-axis. It's a spatial problem that is fundamentally just 1D for ease of visualization. The data are the dots at 5 different locations. And the problem is we want to make an estimate of V-shell at an unsampled location, U0. So at this location here, we want, and it could be any value. We don't know what that value is going to be. We need to estimate that. So the problem we have, though, is we have a trend in the data. You look at that data, and clearly there's something going on. It's rising as we go towards from 1 through location 5. And so there's a pretty clear trend. If you observe a trend, we really should model the trend. We need to fit a model to it. Now, everything we're going to do right now is data-driven. Of course, we could have all kinds of other secondary information, geologic information, geophysical information, picture, so forth, to help us model this trend. So there's a pretty good model. We draw a line, so we have a linear model going through our data right here. And you can see how that could help us make an estimate at this unknown location. That we're accounting for the fact that in this area, things are typically pretty high. If we were estimating over here, we would have things typically pretty low, and the trend captures that information. That's important information. So what we can do is we can now work with residuals. You'll notice the axis here is residual. You'll notice that it's centered on 0, where 0 would be the case where we match our trend, and positive and negative whether or not we were above or below the trend. The residual is captured simply as taking the data values minus the trend. And so you could pan back and forth, and you could convince yourself that within the limits of the quality of my drafting, that we really have just subtracted the trend from all the data values. And then we form a model. We build the model of the residuals. And that model does pretty well. It has a degree of spatial continuity, so at the data locations you get the data values with your model. Away from the data, there's going to be a blending of data and the trend. At a certain distance, you're going to get back to the trend. That'll typically be related to the distance of spatial continuity. That would make sense that when we get far enough away from the data that we don't have any information from the data any longer, we would make the estimate based on the trend. And so we're working with the residuals. And so we build our model in the residuals, and then what we can do is after we model, we can add the trend back. Now this is a pretty good model now, because at the data locations we get the data values. Away from the data we go towards the trend, and it's pretty well behaved. It tracks along that trend very well. What's the consequence of employing this type of modeling approach but skipping the step where we model and fit the trend and work with residuals? Well, if we do that, we're going to have something like this. Away from the data locations, what would be your best estimate? In the absence of a trend, it would be the global mean. Well, the global mean goes something like this dashed line right here. And so systematically, away from the data, in areas of low values, we overestimate. And away from the data in locations of high values, we would underestimate. And so we'd be systematically pretty bad when it comes to our estimates away from data if we don't account for the trend. We don't account for that additional information about the properties systematically shifting or changing. We just leave it to a estimation method with the data. That's not a good idea. Now let me make a couple more comments about trend. We have to identify and model the trend. That's our job. But it's not our job alone as, say, a reservoir modeler. While we discuss data-driven type of trend modeling approaches here and in the additional slides after this, we do that because that's a very practical way we can model trends. And in fact, in many companies, they are using data-driven methods, but they're always within the bounds and constraints of all of the available information to the subsurface asset team. And if this was groundwater, it would be the subsurface team that's dealing with mapping groundwater or uranium or mining. Every time I say reservoir or subsurface, it could be any type of mapping of the subsurface, or it could even be any spatial mapping above the subsurface. You guys know that. I just want to make sure that that's clear. So when we're building these trends, we show data-driven because those are methods that are commonly used, but they are used within the constraints of the entire asset team. And so you have the geologists, the physicists, geophysicists, the petrophysicists, the reservoir engineers, and so forth, who are all incorporating and integrating their information together. There's a lot of different science that goes on to formulating these trends. The trend is in fact very important because it has a direct impact on the resulting uncertainty model. So let's think about this. You have a phenomenon, a variable over the area of interest, porosity, the shale, whatever it might be. It has a certain degree of variability. Now, of course, if it had no variability, it was all the same everywhere, it would be very easy to predict. And that variability actually makes it harder to predict. If you model a trend, what you're doing is you're taking part of that variability. This pie chart represents all the variability, and you are allocating it to a known component, the trend. It's something you're going to model, we'll say deterministically, and you'll treat it as being known. And whatever variability is left is treated as unknown, a residual, and that's part of the uncertainty model. So this is very interesting because you're actually partitioning and removing part of the variance and putting it into a bucket and saying, I know that, but that other component that remains, the residual variance, I don't know that. And just like we just showed the workflow where we subtracted the trend from the data to get residuals, that's exactly what we're talking about here. The variance of the residual versus the variance of the trend, and the total variance before we removed any type of residual. So when we are trend modeling, we're making a conscious decision of how much variability to put in the known bucket and to then decrease the amount of uncertainty. By how much? Well, if the trend and the residual are independent of each other, then it's just simply an addition. The variance total is equal to the variance of the trend plus the variance of the residual, and this 2 times the covariance between the two goes to 0. In that case, this indicates just that x and y are independent. Actually, I just cleaned that up. We would expect that the component of trend and the component of residual are independent, as denoted by the symbol indicating independence. In that case, the covariance between the two would be equal to 0, and we can simply calculate the variance of the residual as the total variance minus the variance in the trend. The more variability you include in the trend, you take directly from the residual the part that's considered uncertain. So when you trend model, you're making a decision about how much variance to put known versus unknown. Now, you might be curious about exactly how we figure out additivity of variance and whether or not, how is that calculated? Well, remember, we previously covered the concepts of expectation. We previously talked about variance. And so, of course, we can denote the variance as being equal to the expectation of the square of the variable minus the square of the expectation, or the mean. And so you can go ahead and do a substitution. Instead of z, you put x plus y. And if you expand and you simplify, you'll find that the whole thing will simplify down to the variance of x plus y is equal to the variance of x plus the variance of y plus 2 times the covariance between x and y. All right, so we know additivity of variance works, and we can use that. We're now thinking about partitioning the total variability between trend and residual. Now, I said the trend was known. And so in that case, we would consider the trend to be a deterministic component of the model. It's a deterministic model that's being used. What is a deterministic model? It's a model that assumes perfect knowledge. There's no uncertainty. How do we generally build deterministic models? They're generally based on knowledge of the phenomenon or the trend that we're fitting, or the trend could be fit to data, but generally it suggests that we have some good information in order to justify this perfect knowledge. Most subsurface models, in fact, have a deterministic component. In my experience, I don't think I can think of a subsurface model I built or saw or reviewed which did not have some type of a trend component to it. Usually a locally variable facies proportion, maybe a vertical locally variable porosity, but of course a trend could include any component. Any statistic could be modeled non-stationary with a trend. What do they look like in practice? Well, they look really cool. They're really quite amazing. Here's two examples I took directly from GoCAD's website from Paradigm. And you can see they're really quite amazing because here's a trend where you have cyclicity in the vertical direction. If you go perpendicular to those dipping beds, you can see that there is cyclicity. You can also see that there's a long range transition from this side to this side, going from high proportion of a facies to a low proportion of that facies. So what do we see here? What do we learn? The trend can actually be pretty complicated. It can be constrained within a gridding framework, which it should be. It could be hierarchical with different directions acting over different scales. You could even have a vertical cycle and then a larger scale vertical cycle imposed, or thinning up, or so forth. In fact, in this documentation, you can see in GoCAD, they're even suggesting the idea of building facies proportion trends by sector and then welding them together over multiple aerial sectors, in which you'd have a lot of degrees of freedom or control over this type of a trend. So in general, trend modeling, they will be quite rich, often incorporating data, incorporating concepts. They would be checked against all of the geologic, petrophysic, geophysical type of information to ensure they're consistent with all of the available information. We must be careful with them because they often are treated deterministically, known, and we only model and treat unknown the residual. Okay, I think I've said enough. I don't need to spend any more time on my soapbox about that. Trend modeling, practically speaking, how could you calculate it? I showed some really beautiful images. One idea is you can just take a moving window and move through the data and calculate the average. What would it look like? Well, in 1D, this is it. This is location, some location coordinate. This is going to be the value of the property of interest. Here's the data values. And you could take a moving window with some type of weight distribution and scan it through the data. What happens with the shaped weight distribution, it looks almost Gaussian, is that when a data value is on the edge, it slowly starts to have more impact. When it gets to the center, it has the most impact, and you're making estimates at this location right here of the trend. And so as you move through, you don't get jumps. If you use a uniform weighting distribution, what will happen is when you get a high value, suddenly, boom, the estimate jumps up. And when the high value leaves the other end, boom, it jumps down. And so that's a pretty erratic trend. You want something smooth. This type of weighting scheme gives you a smooth result. So you move this thing across your data space, take the weighted averages of data and assign them to the center and keep moving across. You'll get a nice, continuous, smooth-looking trend model. How do you calculate trend models in full 3D? Well, it's fine and dandy when you have dense data. Then you can just build a three-dimensional cube, cuboid, or what, and you basically scan through the data set, just like we did with the 1D, but you do it in 3D. Of course, the cursed dimensionality, you would need quite a bit of data to do that, to have the right coverage to be able to accomplish that. So what people do in typical situations where you don't have that type of coverage is they do a 2D plus 1D approach. 2D, what you do is you take all the well data and you calculate the averages, or the vertical drill hole data, or whatever data you have available. You get some type of, you average vertically to get points within a two-dimensional framework. and then you just interpolate between them to get a smooth map. You then average layer by layer over Z in order to get a vertical one-dimensional curve, and you combine them together. You got the vertical trend curve here, x bar of Z. You can scale the aerial trend by that. Notice we've x bar, x, and y. And then you normalize by the global mean. So it's kind of interesting. If you think about it, you can see it a couple of ways. One way to see it is that we're rescaling the vertical proportion based on the aerial map, this ratio of whether or not the trend aerially is higher or lower than the global mean. Or you could shift the global mean over here and see it as a rescaling of the aerial slice by what's going on with the vertical trend relative to the global mean. So you could see it either way. It's a rescaling. And so if you do that, this is what it looks like, a vertical slice. You can see right here. And so you can see the trend features are imposed here. And if you look at a single aerial slice of the trend model, it looks very much like a rescaled version of the aerial trend curve. Okay, let's just do a broad trend definition so we can move forward now. Observation of non-stationarity in any statistic metric of interest. So if I say I see a trend, it means I observe non-stationarity in any statistic over the area of interest. It could also be a model of the non-stationarity in any statistic. This is a trend model. Typically modeled with supportive data, expert knowledge, in a deterministic manner without uncertainty. For the purpose of this course, we'll leave it like that. Of course, you could build multiple scenarios of trend and so forth, accounting for uncertainty, but we don't need to go into that now. But if we're going to talk about trend modeling, we should introduce the concept of overfitting. So what I did was I gave myself a simple one-dimensional example. This is the fraction of fines within some type of a rock. Maybe it's bitumen and oil sands, whatever it might be. We got fines, proportion fines, clays or what. Then we have 8 data, and we have depth. So this is a one-dimensional data set once again, easy to look at, easy to visualize. I built a third-order polynomial using just simple regression fit with a third-order polynomial. We're minimizing the square difference at the data locations, the error squared error at the data locations, and calculate the distribution, the residual. This spread right here would be the amount of variability that I will then model and consider uncertain. Well, the amount of variability represented by this curve will be what I consider certain. Confidence intervals are valuable because it tells me about the confidence in that model just based on data alone, no other information. So that's good to know. Change it to a fifth-order polynomial. I can wiggle. I have more degrees of freedom, more parameters to fit. I can fit the data more precisely. Distribution narrows a bit. I'm claiming to know more. But look what happens. Because of the lack of data, my confidence intervals are growing significantly. So I'm telling myself I know a lot because the residual distribution is starting to shrink, but the model's telling me based on data alone that I don't actually know that much. Now look what happens if I bump that up to an 8th order polynomial. I'm basically one order away from just perfectly fitting the data. Just getting through every possible data value. So 8th order polynomial, where's the confidence intervals? They're off the plot. There's really no certainty about that model anymore. You can see that in fact, this is actually communicated to you very nicely by just consider how it's interpolating between this data point and this data point. Look at that estimate. Do you think that that's not a very robust or reasonable trend value? That's not exactly meeting the property of parsimony, the selection of least astonishment. I don't think so, not very well. Look at the distribution of residuals, very narrow. So what do we have here? We have a model that clearly is unstable. It's communicating to us through the confidence intervals that it has very little prediction accuracy, and the distribution of residuals is very narrow. So if I use that as a trend, I'm going to actually be telling myself that I know much more than I actually know. There's almost no variability left to model as unknown. And so this is the fundamental challenge of overfitting. We have to be very cognizant when we build trend models not to overfit. So definition of overfit, just so we can kind of move forward from that and have something we can share. An overly complicated model that explains the idiosyncrasies of the data, capturing the noise in the data. Also, another way to think about it, more parameters than can be justified by the data, and I'd even open that up and say justified by the available information. Results, likely a very high error away from the data, as shown by the confidence intervals, but results in a very low variance. You are fooling yourself that you actually know more than you actually know, and they will result in a high R-squared, variance explained, that makes sense, little is left to the residuals. They're very accurate at data locations. Almost no variance is left in the residual, but they would do terrible at interpolation testing with a new data set. They would be very bad. Here's another example I took directly from Wikipedia on overfitting. They have a nice discussion about overfitting, a two-dimensional segmentation problem, and you get sense here of capturing data in idiosyncrasies. Clearly, the red and the blue categories have overlap. Many data sets do have overlap. It may be error. It may be some other thing, the other factors you haven't considered, but for one reason or another, in this two-dimensional feature space, there's overlap between these two categories, and we would not want to use the green model. Clearly, the green model is capturing just that data idiosyncrasies, while the black model provides us with a better model that would have better prediction with any type of future testing data set. Okay, so that's all I have to say about the issues around trend. One more time, just because I just have a feeling that this will come up. Of course, we show data-driven approaches right now for the purpose of demonstrating general ideas of trend modeling. Data-driven approaches are commonly used in reservoir modeling, but only under the supervision of subject matter experts who understand the geology, the geophysics, the petrophysics, the reservoir engineering, and so forth, in order to ensure that those are, in fact, informed by all available information. We can have some confidence when we're assigning them to the bin of known versus unknown residual. Okay, so that's trend modeling. Now the next section we'll get into making estimates with simple kriging. We'll do some demos in Excel, R, Python, and so forth. So stay tuned. All right, if you have any questions or comments, go ahead and contact me, email, through Twitter. I'm the Geostats guy. All right, thank you.